Hey there, math problem solvers. Welcome back. Today, we're taking a deep dive into complex geometry, and we're actually going to transform it into a highly visual cheat sheet for you. We're breaking down a masterclass on quadrilaterals and polygons, making sure those tricky mathematical terms are absolutely crystal clear. So if you're looking to turn shape properties from, confusing puzzles into your absolute biggest strengths, you are in exactly the right place.
Okay, let's dive right into this problem solver's journey. Here's our agenda for today's explainer. Section 1 is counting polygon diagonals. Section 2 is unlocking polygon angles. Section 3 covers tricky diagonal properties. And Section 4 is advanced shape problem solving. Let's get to it.
Starting off with Section 1, counting polygon diagonals. Consider this our visual warm-up. We're going to establish the basic geometry of connecting corners. Now, it sounds simple, right? But as the shapes get bigger, the web gets a lot more complex. So, let me hook you with a quick challenge right off the bat. Picture an 8-sided shape, an octagon. Now, imagine drawing lines to connect every single opposite corner to one another, right across the inside of that shape. How many diagonals do you think an octagon actually has? Go ahead, get a number in your head. Boom, the answer is 20. It's a surprisingly huge number, right? Honestly, if you actually try drawing all 20 diagonals inside an octagon on a piece of paper, it literally ends up looking like a wild, chaotic spiderweb. Trust me, I absolutely wouldn't recommend trying to count them one by one during a timed test. And, well, this brilliantly illustrates why memorizing a quick mental cheat sheet is your absolute best strategy. Just look at the pattern. A pentagon has 5 sides and 5 diagonals. A hexagon jumps to 6 sides and 9 diagonals. And then our octagon, with 8 sides, skyrockets all the way to 20 diagonals. You see, you really don't need to manually draw every single line if you just have these relationships locked into your memory. Moving right along to Section 2, unlocking polygon angles. All right, let's ramp up the difficulty just a little bit. We're moving away from simply counting lines and stepping into the realm of calculating actual degree measurements. Now, these two formulas right here, these are the golden keys to solving almost any polygon angle problem you will ever encounter. First, the exterior angle equals 360 degrees divided by n, where n stands for the number of sides. And second, the interior angle is simply 180 degrees minus that exterior angle. Seriously, write these down because they are absolutely vital. Let's actually see them in action. Imagine you're told a shape has an interior angle of 108 degrees, and you need to figure out exactly how many sides it has. Well, step 1, you have to logically find the exterior angle first. So 180 minus 108 gives us an exterior angle of 72 degrees. Make sense? Okay, step 2, apply that first golden key. Divide 360 by 72, and that brings us to step 3, the answer, 5 sides. It's a pentagon. See how smoothly that flows step by step? All right, let's twist it up a bit. What if a problem says the interior angle is exactly 3 times the size of the exterior angle? How many sides does that shape have? I love this one. It's a brilliant word problem because it forces us to mix some basic algebra with our new geometry formulas. So here's how you tackle it. Let's just make the exterior angle x. That means the interior angle obviously is 3x. And since we know an interior and an exterior angle always add up to form a straight line, which is 180 degrees, our equation is simply 3x plus x equals 180. Add them up and 4x equals 180, meaning x is 45 degrees. Now plug that back into our golden rule, 360 divided by 45 degrees gives us 8 sides. Look at that, we found our octagon again. Now here is a phrasing that often tricks students on multiple choice exams. What is the sum of all interior angles of a hexagon, but measured in right angles? Take a second to let that sink in. It's not just asking for degrees, it's asking for the final answer in specific 90-degree units. Okay, let's break this down together. Step 1, we know a hexagon has 6 sides, right? So the exterior angle is 360 divided by 6, which is 60 degrees. That makes each interior angle 120 degrees. Pretty straightforward. Step 2, sum up all 6 of those interior angles. So 6 times 120 gives us 720 degrees total. Now, for the really crucial step 3, we have to divide that 720 degrees by 90 degrees to convert it. And the answer? Exactly 8 right angles. Brilliant work. That brings us to Section 3, tricky diagonal properties. You guys are doing a fantastic job so far. Now, we're kind of shifting gears from strict formulas to theoretical properties. I really want you to pay close attention here, because this is exactly where test questions try to trick you with exceptions to the rules. Let's look at this first question. Are diagonals always equal in length? Well, in a square or a rectangle, the answer is a resounding yes. The lines connecting opposite corners are perfectly equal. But in a rhombus, absolutely not. Actually, if you draw a rhombus on your paper, you'll clearly see it's a stretched out shape. One diagonal line is vastly longer than the other. Now, what's really interesting about this next property is how we can group these shapes by a very specific rule. Do their diagonals intersect at exactly 90 degrees? For a rhombus, a square, and a kite, it's a solid yes. Their diagonals create a perfect perpendicular cross right in the center. But for a parallelogram and a rectangle, the answer is no. They intersect, sure, but definitely not at a 90-degree angle. Okay, how about this property? Do the diagonals perfectly bisect or, cut in half the corner angles? For a square and a rhombus, yes, those corner angles are split perfectly down the middle. But for a rectangle, it's a hard no. Seriously, if you take a ruler and carefully draw diagonals in a rectangle, you will clearly see that the corner angles split into completely uneven, asymmetrical parts. All right, here we go. Section 4, Advanced Shape Problem Solving. All right, take a deep breath. We have officially reached the boss level of today's explainer. This is where we combine literally everything we've learned, our properties, our formulas, and our algebra to solve some complex theorems. Consider this scenario. How do you find the side length of a rhombus if the only information you have is that its diagonals are 16 centimeters and 12 centimeters? No way, right? Well, remember what we just learned a minute ago about a rhombus? Its diagonals intersect at exactly 90 degrees. That single, tiny property is the key that unlocks this whole problem. Because they intersect at 90 degrees, they actually create right-angled triangles inside the shape. So we bring in the good old Pythagoras method. Step 1. Halve the diagonals to get the legs of the inner triangle. That gives us 8 centimeters and 6 centimeters. Step 2. Square them and add them together. So 64 plus 36 gives us 100. Step 3. Find the square root of 100. And step 4. Boom. The hypotenuse, which is the side of the rhombus, is exactly 10 centimeters. You just completely conquered a Pythagorean theorem hidden inside a geometry problem. Let's tackle parallelograms next. Here is your parallelogram golden rule, and you're going to want to remember this. Adjacent angles, the ones right next to each other, are always supplementary. That means they add up to exactly 180 degrees. So the crucial point here is treating this simple rule as the mandatory foundation for any algebraic problem you face with these shapes. Let's see how this builds into an actual equation. Say angle A is 2x plus 25, and the adjacent angle B is 3x minus 5. Step 1, set them up. Step 2, add them together and set the whole thing equal to 180. So 5x plus 20 equals 180. Step 3, subtract that 20, leaving us with 5x equals 160. Step 4, divide by 5. And just like that, a scary-looking algebraic string turns into a simple division problem, giving us x equals 32 degrees. Awesome. Okay, we've arrived at the final ultimate equation test. Imagine a square. Side AB is given as 2x plus 3, and side BC is given as 3x minus 5. How do we find the value of x? I want you to recall the absolute most basic property of a square to crack this one open. Here is exactly how you win this square algebra boss fight. Fact 1, the shape is a square. Fact 2, by definition, in a square, all sides are exactly equal. So, fact 3, therefore you literally just set the two equations equal to each other. Let's solve it. 2x plus 3 equals 3x minus 5. Shift the 2x over to one side, shift the minus 5 over to the other, and you get an instant, incredibly satisfying solution, 8 equals x. The answer is 8 centimeters. You totally nailed it. And just like that, you have officially leveled up. You've successfully mastered diagonals, angle formulas, shape properties, and some surprisingly complex algebra today. You have an incredible, highly visual toolkit at your disposal now. So, my final question to you is, armed with these brand new strategies, which complex geometrical shape will you conquer next? Keep visualizing the math, keep practicing, and I'll see you in the next explainer.